Our main topic today is scalar line integrals. Scalar line integrals. And let's just pick an example from the book. We've got a line segment in number 6. C. C is the segment of y equals 3x plus 2 on the interval from 1 to 2. And we've got a surface f of xy equals 5x plus 2y. And the problem says, find the line integral of this function over this curve with no context. Okay, but I want to bring some context into this. What I want to do is I want to pretend this function, let's pretend this represents, as a function of x and y, the density of the curve as if it were a thin wire sitting in the plane. The mass density of C as if it were a thin wire. Or since it's straight, I could even call it a thin rod. Effectively, it's real thin. It's a line, one-dimensional object, maybe like a piece of hair or something, really thin. And this is the density of that. As if it were a one-dimensional object, the units, if it had units, you'd want it to be mass per unit length, not mass per unit volume or area, because we're thinking of the line as being a one-dimensional object. Say in grams per centimeter, just to pick something. And C, there's my thin wire. Pretend this is a thin wire. What's my goal? My goal is to use, as hopefully you learned a little bit about in Calc 2, an integral to find the mass of the thin wire. Goal, find the mass of C. Let's draw a picture. The line segment C is that function's graph, slope of 3, y-intercept of 2. On 1, 2 means x is between 1 and 2, i.e. x is between 1 and 2, which means y goes between 5 and 8. X goes from 1 to 2. Y goes from 5 to 8. The line segment C is this one here. As in Calculus 2, we can think of this intuitively in terms of tiny little chunks. Slice up this thin wire, which happens to be straight in this case, but in general could be a curve. It might not be a straight wire, it might be a curved wire. Slice it up into little chunks of a certain small length. We're going to call the small length not dx, not dy, but ds. This is a tiny arc length. You might call it an infinitesimal arc length. In centimeters, say. What's the mass of the tiny chunk? The small mass, dm, of the tiny chunk should be the density in grams per centimeter times the length of the tiny chunk in centimeters. The value of the function f times ds. It's going to be helpful to think of this along this curve as being a curve parametrized by arc length, meaning we're going to ultimately think of this as a parametric curve. We aren't yet. We're thinking of it as a graph of a function. Think of it as a parametric curve where S represents how far along the curve you've gone. And we're going to think of this conceptually as f of s, where s is arc length along C. I can be a bit more explicit about this, but not at the moment. At the moment, I'm just going to write that density function as f of s. F of s times ds is the small mass. And that means the total mass is found by adding those up, integrating them. Integrating f of s ds. Over what? Over the curve. And just as with double and triple integrals, we put the region, the domain, underneath the integral. So we're going to put the curve under the integral and a little bit to the right. C. All this is a so-called, what I call at least, a conceptual equation. Conceptual equation. It's not an equation that helps you compute it, but it can help you understand it. You imagine the integral as being adding. You imagine the dm's as being tiny masses. You're adding up the tiny masses to get the total mass. Those tiny masses themselves can be thought of as products of densities in grams per centimeter times lengths in centimeters, giving you a quantity in grams. The units would be grams for the f of s ds and also for the integral. But that begs a question. How do you actually do the integral? Let me see if I can do it by parameterizing by arc length. First of all, if I come up with any parameterization of this, I can use that parameterization to find a parameterization by arc length. So again, it's this line over that, or those values of x. One parameterization is just to use x as the parameter. Maybe to emphasize it's a parameter like time, I'll call it t instead of x. One parameterization of C, maybe the simplest one, is x equals t, y equals then 3t plus 2, as t goes from 1 to 2. In vector form, i.e., that would be the vector r of t has components t comma 3t plus 2. It's a linear parameterization. That's nice. And that's going to mean the velocity vector for this parametric curve is constant. This implies the velocity vector, which is the derivative of the position vector, is constant 1 comma 3. And it also would imply the acceleration vector is 0. That also implies the speed as a function of t, which I could also use the shorthand notation cursive v of t is constant. And it's square root of the velocity vector dotted with itself, just to remind you of some things we did in the past. It's square root of 10, in fact. It's constant, it doesn't depend on t. That also leads us to say the distance traveled function, arc length as a function of t. By the way, the speed is also, this is also the length of the velocity vector. The distance traveled is the integral of the speed. Use a different letter like tau. But this speed is constant at square root of 10. So the integral is pretty easy to do. Get square root of 10 tau. Tau goes from 0 to t. And in the end, that simplifies to square root of 10 times t. If we take this equation, the equality between this, and solve for t in terms of s, t is s divided by square root of 10. We can then use that along with r of t to find a parameterization by arc length. This is the method. If we can now use this to create a new function, I'll call it R1 of t, or excuse me, R1 of s, by using the original parameterization R of t and replacing t with s over square root of 10. And if we do that, using the formula for R of t right there, replace those t's with s over square root of 10, we get s over square root of 10, comma 3s over square root of 10 plus 2. That is a parameterization by arc length, which intuitively means as you plug in different values of s, you're moving along the curve at a unit speed. The length of the derivative of this is 1. I mean, we can verify that. R1 prime of s is the constant vector, 1 over square root of 10, 3 over square root of 10. And its length, its norm or magnitude is constant at 1. It's a unit speed parameterization, also called a parameterization by arc length. How is this helpful? What in the world was I doing this for? To try to compute this integral. Because now I can figure out what f of s is and let s go from 0 to square root of 10. This parameterization was from 1 to 2. Oh, wait a minute. I guess we'd have to go, t goes from 1 to 2. I had to figure out the right limits for s. You know what I should have done? I should have made this a 1 instead of a 0 there. Sorry. Can I make an adjustment here? I think I can still do this maybe. Let's see if it works. T goes from 1 to 2. That's equivalent to s over square root of 10 going from 1 to 2. So s itself goes from square root of 10 to 2 square root of 10. I think that'll be the interval that we need. What is f of s? F of s is this function where you replace x with the first coordinate of R1, first component, and you replace y with the second component. This is not the way you're going to typically compute these things, but I'm trying to make a conceptual point. So I'm going to replace in the formula for f, x with s over square root of 10, and y with that. In the end, if you simplify this, you get, let's see, 2 times 3 is 6, plus 5 is 11. 11s over square root of 10 plus 4, it looks like. That should be the function to integrate to get the mass of this thin rod, this wire, as s varies from square root of 10 to 2 square root of 10. There's a better method. Hang with me here. Hopefully I did not make a mistake. Square root of 10 to 2 square root of 10. That's the limits on s of the function 11s over square root of 10 plus 4. I hope that's right. Okay, what is it equal? It's about 64.83. What's the better way to do this? And hopefully I get the same answer, because if I don't, then I'm not sure where the mistake is. The better way to do this is to avoid parameterization by arc length, but instead use it as an idea. This equation effectively says, by the fundamental theorem of calculus, that ds dt is the speed at time t which is the length of the velocity vector, which is the length of the derivative of the position vector. And therefore, that equation is equivalent to saying ds is the length of the derivative of the position vector dt. And what that ultimately means, this is the way you want to do these calculations, is that the value of the line integral, the scalar line integral, can be computed by replacing s with r of t and replacing ds with that, the magnitude of r prime of t dt, over the interval for t, which is 1 to 2. And r of t is our original parameterization. That was simpler than the arc length parameterization. T comma 3t plus 2. Square root of 10s are going to be unavoidable. The derivative of that is 1, 3, and the magnitude of the derivative is square root of 10. That makes me happy because it makes me hope that I got the right answer before. Square root of 10s are going to be unavoidable. As far as plugging r of t into f, you do the same kind of thing we did here. Replace x and y with those two parameterizations. So I end up doing 5x is 5t plus 2y is 2 times 3t plus 2. That gets multiplied by square root of 10. And that's the integral that I got to do. This simplifies to 11t plus 4. This is feeling positive, so I'm seeing similar kinds of numbers here. In the end, you're going to get a square root of 10 in front. Integrate that, you'll get 11 halves t squared plus 4t. T goes from 1 to 2. So what is that going to be? Square root of 10. We'll have an 2 squared is 4 times 11 halves will be 22 plus 8. I'm plugging 2 into there. Minus, plug in 1, I get 11 halves plus 4. That's a 30. This is, well, that's a 19 halves. 30 is the same as 60 over 2. So it looks like I get 41 square root of 10 over 2. Is that the same thing? It looks like it's a possibility. You know, these square roots can be written in different ways. 41 times square root of 10 over 2. Yes, so happy. Okay, the second way is the way you want to do it. But I did it the first way, partially to show you get the same answer, and partially to emphasize that, theoretically speaking, that's what's really going on in the background. Is when you write it in this way, S is an arc length parameter, is what I'm trying to emphasize. So if you want to do it this way, you have to parameterize by arc length. That's always very tricky. Again, I probably here should have done the integral from 1 to t instead of 0 to t, because in the ordinary parameterization, time was starting at 1 instead of 0. I was able to shift the limits of integration, and I got the right answer anyway. But it would have been nice to do that to start with. At time 1, you've traveled 0 distance, is what would have been maybe better. Well, by the way, I should also make another conceptual point. This answer does represent, yes, the mass of the wire. And you'll also see in the book, you can figure out center of mass of the wire, which is not necessarily on the wire, though it would be in this case because it's straight. You'll see these formulas for center of mass in the book as well. But it also represents, the answer represents an area. It actually represents an area under the graph of the surface, which is the density function, and above the curve. So if you, for example, made a plot 3D of the function f, which was, again, 5x plus 2y, above this line, you are finding an area under the surface above the line. Now, I haven't drawn the line in there. Could I do that? Yeah, I think so. I can add a parametric plot, 3D, and parameterize that line in the XY plane as t, comma, 3t plus 2, comma, 0 for the z coordinate. T goes from 1 to 2. It's down there. A little hard to see there. See that line there? The answer represents the area, not volume, area under the surface above that line. Okay, so you can interpret it geometrically that way too, and that's something the book emphasizes.